Okay, so the next two examples just involve a little bit of factorising. So just to convince yourselves that you're okay with this. So given that z equals 2 plus I is the root of this quartic, we can look at solving the equation. You could use a roots method to solve this and get simultaneous equations, and that would be fine, but just to give you an alternative way through, I suppose, or something to think about at least. So z equals 2 plus I is a root, implies that z equals 2 minus I is a root. So that's because they come in complex conjugate pairs. And then we can find a quadratic with roots 2 plus I and 2 minus I. And then we can divide the quartic by the quadratic to get another quadratic and then solve that using the quadratic formula. So slightly different method. So finding a quadratic with roots 2 plus or minus I. So we know that the sum of alpha will be 2 plus I plus 2 minus I, which is 4. The product of the roots, 2 plus I, 2 minus I, is 4 plus 1, which is 5. And so z squared minus the sum of the roots times z plus the product of the roots. So what I can do now is I can divide this quartic here by the quadratic. I'm not teaching long division per se as part of the course because you don't actually need it. So we can do this by inspection. So I'm dividing by z squared minus 4z plus 5. And then it's the same method as you've done in maths. So to get the z to the power 4, I need to do z squared times z squared. And there's only two places you're going to get a cubic term. It's going to be here and here. So I've got minus 4z cubed, and I don't want any more z cubed. So it's going to be plus 0z. And then 5 times 1 is 5. You may get a middle term on a different factorisation. And then you can check if you want to. So you've got 5z squared plus z squared is 6z squared minus 4z minus 4z. And then z squared plus 1 equals 0. So it's possible you'd need to use the quadratic formula here. It may factorise and give you real roots. This one here is nice and easy to solve. So z squared equals minus 1 and z is equal to plus or minus I. So remember the plus or minus when you square root, and then you've got your complex conjugate pair as well. So the roots are 2 plus I, 2 minus I, and minus I. So just to give you a different method to think about, but again you could have looked at doing sort of sum of the roots and the sum of the pairs of the products, sum of pairs of triples, all of them multiplied together. You could have sort of worked with those things to find the other two roots, a couple of those, but yeah, you could also factorise. And then one more example. So, for example, solve z to the power 4 minus 3z squared minus 4 is 0. Now this looks like the ones that we were doing in maths when we did the quadratics in disguise. So there's no z cubed and there's no z term, and so this will factorise relatively easily, this particular one. So we can let w equal z squared, and then we've got a quadratic in w. And this one actually factorises. And so w equals 4, or z squared equals 4, because w equals z squared, or z squared equals minus 1. And so z is plus or minus 2, or z is plus or minus I. There isn't any reason why I've got plus or minus I on both my examples. So that's that quartic solved. In a similar way to the ones we're doing in maths, we're just picking up complex roots as well. So if you could have a go, please, at doing page 64, exercise 3.4, your favourite exercise, and question 8, which is similar to that first example I just did a minute ago, and question 10, and then question 14. And if you want to challenge, you can go past 14 as well, but they're kind of the ones to focus on. So I'm hoping it all goes all right. Any questions about today's lesson, you can ping me a message and I'll try and pick that up at some point over the next couple of days. But yeah, see you Monday. And yeah, hope all that goes well.